All right, welcome back. Today we're digging deeper into a really powerful idea from Thomas Kuhn's landmark book, The Structure of Scientific Revolutions. So, let me ask you a question. What do you think a scientist actually does all day? When you picture it, it's probably some lone genius in a lab just waiting for that one big eureka moment, right? The kind of thing that completely changes everything. But here's where Thomas Kuhn steps in and says, hold on a second. He argues that for most scientists, most of the time, it's a lot less dramatic than that. It's not really about constant revolution. It's much more about dedicated puzzle solving.
Kuhn actually has a name for this whole puzzle-solving thing. He calls it normal science. And to really get what he means by that, we've got to first understand the box that the puzzle comes in. The framework that sets all the rules.
So this framework, that's what Kuhn famously called a paradigm. And the puzzle box analogy is perfect. The paradigm is like the picture on the front of the box. It's the whole set of theories, laws, and assumptions that everyone in a scientific field pretty much agrees on. For astronomers after Newton, their paradigm was his laws of motion and gravity. It laid out all the rules, and, this is key, it guaranteed that for every puzzle, there was a solution.
And that brings us right back to normal science. It's simply the day-in, day-out work of fitting those puzzle pieces together. The whole time, you're assuming the picture on the box, the paradigm, is correct. The goal isn't to challenge the rules, it's to use them to fill in the picture, to refine it, expand it, and just make it more and more precise.
Okay, so that's the big idea, but you're probably wondering, what do these puzzles actually look like in the real world? I mean, if scientists aren't out there trying to start revolutions, what are they spending all their time on?
Well, according to Kuhn, the whole thing breaks down into three main categories. These are the kinds of puzzles that really drive the day-to-day work of a scientist.
So what are they? First, you've got measuring key facts, the stuff the paradigm says is really important. Second, you're trying to match those facts up with what the theory predicts should happen. And third, and this is a big one, you work on articulating the theory itself, basically making it clearer and more powerful.
Let's dig into that first one, measuring key facts. At its core, this is all about getting the numbers right. The paradigm points to some fundamental constant in nature and basically says to the scientific community, hey, this number right here, it's super important. Your job is to go out and measure it as precisely as you possibly can.
A perfect example of this is the universal gravitational constant. After Newton came up with his laws, scientists knew this number had to exist, but for about a century, nobody could actually measure it. The puzzle wasn't if the number was there. The theory guaranteed it was. The puzzle was the insane technical challenge of building something sensitive enough to find it. See? The goal wasn't to question gravity, it was to make the theory of gravity even better.
Okay, so the second big puzzle is all about matching facts to the theory. This is where scientists work to show that what the paradigm predicts is actually what we see happening in the real world. And this gets especially tricky when you look at new or really complex situations.
Take Newton's laws again. They worked like a charm for predicting the orbit of, say, the Earth around the Sun. But when you looked closer, you'd see the planets didn't follow those paths perfectly. Why? Well, because they're all pulling on each other too. The real solar system is this chaotic dance. And for decades, some of the most brilliant mathematicians on the planet, guys like Euler and Lagrange, wrestled with this massive puzzle, how to apply Newton's laws to that whole mess. And you know what? They eventually nailed it, showing an absolutely stunning match between the theory and what we actually see in the sky.
And that brings us to our third, and you could argue most important, kind of puzzle, and that's the work of articulating the paradigm.
Now, articulating sounds a bit academic, but it's really about making the paradigm a better tool. It's not just one thing. It could mean clearing up some fuzzy ideas left in the original theory. Or it could be trying to apply the theory to something totally new. And sometimes it even means completely rewriting the paradigm to make it more elegant and way more powerful.
Here's a great example. Back in the 18th century, a big idea was the caloric theory of heat. Basically, they thought heat was a type of fluid. So a major puzzle for scientists at the time was, okay, if heat is a fluid, can we use that idea to explain new stuff, like why a gas gets hot when you compress it? When they figured it out, it did more than just explain that one thing. It made the whole heat is a fluid paradigm seem much stronger and clearer.
And then you have reformulation. This is amazing. You have these mathematicians, Lagrange and Hamilton, who looked at Newton's mechanics. They didn't prove him wrong, not at all. Instead, they basically rewrote his work in a completely new mathematical language that was way more powerful and elegant. And suddenly, the Newtonian paradigm could be used to solve problems that Newton himself probably never even dreamed of.
Okay, so let's recap. You have this incredibly intense, super focused, and honestly, very successful process of just solving puzzles. And it's all built on one core belief, that the paradigm is correct. But, and this is a huge but, that very focus, that dedication, leads to something really profound and totally unexpected.
See, if you're a scientist doing normal science, you are all in. You have to believe that a solution for your puzzle exists, because the picture on the box, your paradigm, guarantees it. So if a piece isn't fitting, you don't think, maybe the picture is wrong. No way. You think, I'm just not being clever enough. It's my failure, not the theories.
But what happens when a piece just won't fit? What happens when a puzzle fights back, and no matter how brilliant you are, you can't solve it? This, right here, is the critical turning point. Because the very thing that makes normal science so powerful, its obsession with precision, its drive to make every tiny detail fit perfectly, also makes it incredibly good at finding that one piece that, no matter what you do, just doesn't belong.
And that is the great irony at the heart of Kuhn's whole idea, that this rigorous, detail-oriented, you could even say conservative work of normal science, that's the very engine that uncovers the huge problems, the anomalies, the unsolvable puzzles that kickstart a scientific revolution. It's the slow, steady, methodical work that, in the end, is what actually changes the world.